Let's take a look at a couple of imaginary numbers. What I mean by imaginary numbers are any number that includes the imaginary component I. Now, in previous classes, you should have learned that I stood for the square root of -1. The reason that's imaginary is because you're never allowed to have a negative in the square root. So anytime we have a negative in a square root and we want to still use that number, we can go ahead and change that square root of -1 into an I. And complex numbers are numbers that are made up of a real component and an imaginary component. So typically they're put in the form of a plus bi, where a is your real component and b is your imaginary component. And this form actually has a name. This form is called your rectangular form. So your rectangular form, again, has that real component and the imaginary component. So an example of a number that would have that real and imaginary is 3 plus 4i. Now we can also graph complex numbers. And in order to graph a complex number, you have to have a complex plane. And the complex plane looks a lot like your regular coordinate plane. But instead of an x and a y, you've got the real and the imaginary. So in this case, our real component is 3, so I would have to move over 1, 2, 3, and our imaginary component is 4. So 3, 4 is how I would graph this on the complex plane. 1, 2, 3, 1, 2, 3, 4. That would be this point. But we can also go into negatives and other locations like that. It's not just all first quadrant. If I had the point -4 plus 3i, then the real component is -4 and the imaginary component is 3. So in this case, I would go over 1, 2, 3, 4, up 1, 2, 3, and there's that point there. Let's take a look at a couple of other things you can do with complex numbers, but in order to do that, I have to grab one of these. So I'm going to hold on to this one. And I'm going to go ahead and erase all this other stuff. Get out my big eraser here. So one thing that I can do after I've graphed it onto that complex plane is I can find out something called the modulus. So we can actually figure out what the modulus of this vector or of this complex number is. And let's go ahead and give it a name. Let's go ahead and call this p. This is the complex point p. So modulus is a fancy word for norm, which is another fancy word for magnitude, which is, again, another fancy word for the absolute value, specifically when we're talking about complex numbers and vectors. So one thing to keep in mind with the absolute value is a lot of people believe that it just means change the number to positive. But the absolute value actually means that you're finding the distance from 0. So on your coordinate axes, that is your 0. That's your origin. And we want to know physically how far away is our complex point. Well, we traveled 4 units to the left, and we traveled 3 units up. And if you graph that out, you can see that you've got another right triangle formed, which is very, very similar to what we did with vectors. And if we wanted to find the magnitude of a vector, then we would use Pythagorean theorem. So the modulus of p is equivalent to the absolute value of p, which is where we're going to use that magnitude formula, where you take 4 squared plus 3 squared, do a little bit of algebra, 16 plus 9 will give you 25, and the square root of 25 is 5. So the modulus, or the length of this vector, or complex number, apologies, is going to be 5. Well, the other thing that we can find with complex numbers is going to be your direction. But when we're dealing with complex numbers, we're actually going to call it something else. Instead of the direction, we're going to call it the argument. So the argument of p is equivalent to the direction of p. And if you think back to how you found the direction of vectors, then you means you break this into a right triangle. So when I break into a right triangle, just like I did to find the modulus, I'm going to find this angle right there. So using a little bit of SOHCAHTOA, you can look back at the previous videos to figure out how we got that. But we're going to find out that the angle theta is equal to the inverse tangent of y over x. And when we plug that into our calculator, let me go ahead and take a little second to do that. Inverse tangent of 3 over 4. When my calculator's in degrees mode, I end up with 36.870 degrees with a little bit of rounding. Now remember, that's this angle here. So if I want to find the argument of my complex number, I end up having to do 180 minus that angle I just found, because that angle I just found is the reference angle. So 180 minus that previous answer gives me 143.130 degrees. And that ends up being my final argument for P. So complex numbers are made up of a real component and an imaginary component. And in order to graph those on your complex plane, you've got your real component on what we call the x-axis, and you've got your imaginary component on what we call the y-axis for a regular coordinate plane. We've also got the modulus that we can find, which is a fancy word for the length when you're dealing with complex numbers, and we can find the argument, which again is a fancy word for direction when you're talking about complex numbers. So in this case, we could also define this complex number, instead of putting it in rectangular form, we could put it in polar form. So your polar form of a vector is when it's r cosine of theta plus I sine of theta, where r is your magnitude and theta is your direction or argument. So for our example here with P, our polar form is going to be 5 times the quantity cosine of 143.130 plus I sine of, I'm going to run out of space, let me grab a little bit over here, sine of 143.130 degrees. Now that is a big old mouthful to say and a lot to write down, so it turns out we can simplify it just a little bit. Because we use this so often, some people came up with a shorthand for it. It's called the cis function, C-I-S. So that stands for your cosine, your imaginary, and your sine. So if I wanted to write this in the shorthand polar form, I would still put the magnitude, but then I'd shorthand those cosine, I, and sine, and then I'd put in my direction. So now we've got our polar form in the long version, and we've got our polar form in the shorthand version.